Hello. Remember this? That was Monday. Today we're going back to revisiting force and friction, and you'll have this PowerPoint and the slides now to take your notes as you've gone through them Monday, Tuesday, and Wednesday. I don't have a lot more to add now, but I am going to share the screen so you can see the last of the slides. Whoops. So you've gone from slide 1 to slide 18. And now, types of forces. These are pretty self-explanatory. And when I say self-explanatory, what I mean is just read through the slides carefully. Everything you need to know is there and should be a review of the introduction to forces you received on Monday. So contact forces, we had friction, we've had gravity, we had push, and we had pull. Okay, so write these definitions and think about these. Unfortunately, we're not in class to express spring force and air resistance and tension. These are all, but they will be in the mini labs you can do at home, and that'll be posted as well. And you'll go through these types of force. We talked about skydivers and gravity and air resistance, but spring force is an interesting one. There's a lot of engineering and applications, mechanic applications to springs, everything from the shocks on our cars. Any vehicle that has to absorb impact is going to have spring force and the coils, and the amount of weight they have to hold and that they allow to cushion that ride has to be carefully engineered by the thickness and the type of metal used, the hydraulic or the air compression used. So springs can either be compressed like a slinky is, or they can be kind of like a pin, a click pin that has a very small spring. It's designed not to be compressed, but to resist compression. So go through the types of forces. These are all contact forces that can be the applied, the normal force. This perpendicular to surface, all that means is this, right? That is perpendicular right there. So what we're talking about really is the ground that you stand on. So if this is you and this is the ground, the normal force that the ground exerts pushing up on you is called normal force. All right. Applied force is the push or pull, one direction or the other, whenever you push it. Frictional force is the drag. We know that one. Tension, equally and opposite, tug of war. We've talked about each of the others. Now, non-contact forces are like magnetism. I briefly mentioned that in Monday's lecture. Remember when I held up a hand, I talked about motion in a straight line, but there's a magnetic force. It could curve or bend it because of the attraction there. And that's how we got orbital motion. So gravitational force is an attractive force between objects. And this is probably the one I will talk about just a little bit today. Weak and strong nuclear forces, we're just not ready for those yet. Mama and Papa didn't. It's kind of like, you're not ready for that talk. If you really want to get into the physics, here we can. But here we're talking about forces at the atomic level. They're not practical for us to talk about. They're really forces that play a role in the nature of the universe. So they're very strong. You're talking atomic bomb here, things like that. But these right here, these 4 non-contact forces govern the entire universe. Pretty crazy, eh? As a matter of fact, they're looking still for one unifying explanation that pulls all these 4 forces together. And the only one put forth is the most ridiculous one, and that's string theory. But that's for another year. Going on. Friction and gravity. So 2 forces that can always affect the motion of an object. You've read about this. That was Tuesday's lessons all day. So go back and review some of those if these slides are not familiar to you. But just slowly read through here. Look at this kind of motion. The friction dragging, normal reaction pushing up, the weight pulling down because of gravity. So for a quiz, just to give you an idea, you would have an image or a diagram that's not labeled, and I would have you label the arrows or add the arrows. This is what you would also do in lab to help prepare you for this. We can't reproduce that in lab, but I may put on a Flipgrid. I did record some videos, but I haven't figured out how to get it on Flipgrid yet, so I'm gonna have to redo it. And what you would do is simply identify the forces and the concepts that we've talked about, like momentum, inertia, things like that, forces, and the direction of those forces. So anyway, get to know these types of pictures and associate the type of force that is acting upon, and whether it's a contact force or non-contact force. If you need to hear me say all that again, just stop, rewind, and listen to me say it again. What affects the amount of friction? I talked about this in the cartoon lecture yesterday when the girl is pushing the one box. All right, and then same amount of effort would push two boxes only half the distance. Why? Well, there's more mass. It's simply heavier, and I think we all understand that. We've experienced it in life. The harder you push, the longer it's going to take friction to stop the object. So you push real hard, you're overcoming a lot of friction, you're going to go further. You push softer, not as much work going into it, it's not going to go as far. The friction will overcome. Now, even within friction, and we're just touching the surface here, there's all kinds of friction even at that, whether it be rolling, sliding, gliding, the friction on ice versus wheels on a ramp versus rubber tires on a street. There's a chemistry to all of this. Our highways are not made the same way as our neighborhood roads are, right? Because of the amount of water, the amount of traffic, and the kind of frictionless surface that's needed for that. So the rougher the surface, the more friction. And then, of course, the weight of the object, the more friction. And that's what this picture is showing right here. A would be harder to move than B. So this is one that might take a little while. And if you don't understand it, this is one I would say you're okay. Just memorize it. Okay? And that is gravity. If you walked into, let's just say, the Excel Center in the Commons, that's a pretty big area. Now, if someone were standing on the other side of the room and you came in at the doors and each of y'all were just kind of waiting for class to start, because y'all are so far apart, there's not a likely chance. I mean, you might throw a hand and say, hey, you might yell, good morning. But most likely, you probably wouldn't say anything because you're not close to each other. You're at distant proximity. The attraction of those of two people at that distance to talk to each other is minimal. But if someone was sitting in that first seat by the door leading to the classrooms and you walk in the front door, you know, and you're kind of wandering around, you're going to come in close proximity. And the closer proximity you are to somebody, the more likely you are to bump shoulders or even say hi. How's the weather today? Well, another day, another dollar. You know, you're likely to strike up a conversation just because you're close to each other. So if you think of that as an analogy, the force of attraction between all objects. So the amount of gravity depends on two things, the object's mass and the distance between the two objects. We might say how well you know the person and how far away physically or close to them physically you are at the moment. Those two things would cause a reaction or not. So if you look at this distance here, you have mass 1, quite a bit smaller than mass 2. And at this particular distance, there is a certain amount of attraction. Most of these forces go back in. You have to apply them to earth science. If you remember the astronomy unit in the beginning of the universe and how we talked about the force that expands, the expansion, and the contraction. So gravity is a force that acts between any two masses. Everything has its own gravity and attraction. No matter how small, sometimes we can detect it. So two factors affect the gravitational attraction between objects, mass and distance. And if you look here, the force of gravity is acting between these two. But these two have such a small mass and they have this much attraction. You see the vector arrow here? They're probably not going to collide with each other anytime soon. Other forces would have to act to get them closer. So at this distance, they're safe from ever colliding, like many of the stars in our universe. The force of gravity the force of gravity acts between all objects. Now, same distance, all right, same distance, but larger mass. The larger the mass we've found, the more likely they are to collide. So look at the vectors here. Because of the mass is larger, the vectors are larger, and these two probably will make contact with each other. And then lastly here, if mass increases, the force of gravity increases. And lastly, if distance increases, the force of gravity decreases. So we're at the same mass, and now we're further distance. These have an even weaker. So look at the arrows up here. At least those are pulling towards each other. Over time, they might come close to each other to make contact. These would take a much longer time to make contact because the force of attraction is much weaker because they're so far apart. This is not hard to imagine, really, if you've ever played with magnets. And depending on the type of magnet you have, sometimes you can feel the force, you get them close enough, and they snap together, and you pull them apart. And some magnets, like stereo speakers, even from this distance, you can feel the pull, and they would pull together. So the bigger the magnet, the bigger the force of attraction, the quicker they'll come together. All right, so this is probably the most challenging slide right there. And again, we're talking about nature of the universe here. And since Earth is so large, everything on it is attracted to it. Even if they're not touching, it's attracted to it. Like satellites. This is, T-Mobile, AT&T, Sprint. Everyone has satellites up there. Why aren't those satellites drifting off into space? Well, they're held in orbit by Earth's gravity. So another example is throwing a ball. If you throw a ball up, but gravity pulls it back down to the Earth. We saw that Monday, right? So you can counteract gravity by catching the ball before it hits the ground. You provide the outside force, right? So Earth being so massive compared to most things we come into contact with, it is not going to allow us to escape its orbit. All right, so this will describe that movement of centripetal force, Earth, velocity. These are all moving in what would be typically called a straight line, a vector velocity. But due to that change in velocity and the acceleration, it continually falls in a circle. And that's what's called the orbital motion. So read through this slide carefully. You can pause me if you need to. Now, all these formulas, and don't get scared, all these formulas should start to look pretty familiar. The density formula was like this. Average speed formula was like this. And now we have the net force. So we want to know how to figure out how much force would it take to move this car at a certain speed for a certain distance. We can do that quite easily. And this is a very popular formula. You might have seen it in one of the videos, but F equals ma. Force equals mass times acceleration. These values are typically given to you. You can weigh the mass and you can time the acceleration. If you can do that, then when you multiply these, you get the product, and that's the amount of force. Typically measured, as you know already, in newtons. Newtons is the SI unit for force, or kilograms mass per second. Okay, so here are some examples you can look through. I'm most interested in the net force. We may get into work next week when we do energy. It will apply directly, but look here, this is going to be a derivative. So you see force is in this equation times distance. So if we know the mass and the speed, which are easy quantities to come by, we can measure mass and we can time the acceleration. So if you can do those two things, you can figure out force. And if you can figure out force, you can put it in to the distance, which is also measurable. And now you figure out work. How much work was actually done. Now we'll get into defining work Monday of next week as we get into energy and energy conversions. These triangles are just ways to remember how to solve for the variables. So if this is speed, to find speed, you divide distance by time. To find time, you divide distance by speed. To find the distance, you multiply speed times time. So that's what these T's, this cross, allows you to do. Okay. Again, looking at force. To find the force, what do? Well, M and A are next to each other, so mass times acceleration. All right. Spend some time looking at that. If you don't get it, that's fine. on any kind of quiz, I would always give you the equation. You would just need to plug in the numbers. All right. Try those practice problems, and we'll see you again soon. Ciao now.